Hi everyone, I'm John Wei from Georgia Institute of Technology. Today I'm going to discuss cross-modal joint embedding with diverse semantics. We already open source our work on GitHub. So what is a cross-modal retrieval? Cross-modal retrieval is a retrieval task across different modalities, such as image text cross-modal retrieval. Here we take the cross-modal retrieval between the cooking recipes and the food images as an example, as shown in this figure. Given a recipe query, we want to find the top matched food images. Similarly, given a food image, the cooking recipes with the highest relevance ranking are retrieved and the matched one is ranked as top one here. The benchmark dataset used in this work is recipe 1 million dataset. A recipe example and the two associated food images are listed below. We can see that a cooking recipe consists of a title, list of ingredients, and the cooking instructions. Following pre-processing in existing works, duplicated recipes without images are filtered out, and the remaining are split into training, validation, and testing sets. The accuracy results of the existing works on recipe 1 million dataset are reported in this table. Image-to-recipe retrieval and the recipe-to-image retrieval both are evaluated in this work. We can see that the accuracies of most current works are quite low, and the NSJE significantly improves the performance. Here, we show the recipe-to-image retrieval result of JESR and the NSJE based on the same recipe query. The recipe is a kind of tortilla wrap. Most of the JESR top results are hamburgers images, while NSJE approach ranks the matched image as the top two, and succeeds to return the tortilla wrap images as the top results. Here are the corresponding common latent space figures of JESR and NSJE. Concerning the previous example, the matched image, denoted as the red cross, is far away from the recipe query, denoted as the centric red square in the JESR result, which indicates JESR doesn't map the recipe and the food images into the common space properly. As for the right figure for the NSJE approach, the matched image is very close to recipe query embedding. Since NSJE incorporates multiple semantics in the joint embedding learning, that's why NSJE can get much better results. Therefore, in our work, we want to get a deeper insight into the impact of diverse semantics on the quality of cross-modal joint embedding. To achieve this goal, we present a holistic evaluation framework to study and evaluate the cross-modal joint embedding learning by incorporating diverse semantics in recipe embedding, image embedding, and joint embedding learning respectively. The general approach for the cross-modal retrieval is to train a joint embedding model that maps text-image pairs into the joint latent space where the textual and the visual embeddings can be computed and compared. The training can be roughly divided into two steps. Step 1, we need to learn the feature maps of cooking recipe and the food image respectively, and then map the embeddings of recipe and image feature maps onto a d-dimensional joint latent space. Step 2, calculate the similarity score between the two embeddings, and then employ the loss function to perform the joint embedding loss optimization and update the parameters iteratively. Now start with the image embedding approach. Most of the existing works resort to CNN networks as image encoder. For example, SAN system learns the image embedded by VGG16 networks, while JESR, ANSR, ADMI, and ACME all leverage ResNet 50 networks without incorporating any semantics. Unfortunately, the neural features learned directly from the pixel grid of food image fails to capture the fact that the food images corresponding to a cooking recipe may have different visual appearance due to different ways of using ingredients, different decorations, and background. NSJE addresses this problem by extracting the image category semantics from the food images by leveraging the food11 classifier to iteratively align the image embedding closer to the associated recipe embedding in the common latent space. Here, we want to study the impacts of using different CNN networks as encoder to generate the image embedding and different ways of adding the image category feature. The table below shows the results. To make a fair comparison, we use JE model in JSR work, which doesn't leverage any semantics in the joint embedding learning, only varying the CNN encoder to change the image embedding. We observe from the results that utilizing ResNet 50 networks as a CNN encoder for image embedding works more effectively than VGG16 networks. And when the dimensions of image feature and the food11 image category feature are set to 2048 and 300 respectively, the training of the joint embedding model seems more effective for recipe 1 million dataset, which is set as default in the following box. This figure provides a visual example by comparing JE baseline and JE plus food11 image category semantics. The predicted food11 categories are listed below the top 5 retrieved images. For the risotto recipe query on the top, the JE plus food11 image cat approach returns the food images about the risotto as the top 1 result. In comparison, using the JE approach, the matched image is returned as the top 10 in the query results. A similar observation is also found in the image to recipe query, showing again that leveraging the image category semantics can help to boost the performance of cross-modal joint embedding learning. Now we come to the recipe embedding. The table below summarizes the main feature engineering techniques of the existing approaches on recipe title, ingredients, and cooking instructions for recipe embedding. Most of the current approaches encode the recipe embedding by LS10 or GRU to leverage the sequence feature in the recipe text without incorporating any other semantics. NSJE argues that discriminative ingredients in the recipe can be regarded as the keywords to distinguish its recipe from other recipes. Therefore, TF-IDF approach is used to find the discriminative ingredients in the recipe text. To study the impact of leveraging TF-IDF semantics, we conduct a set of experiments based on the JE model and only change the recipe embedding approach. The table below shows the result. We observe that extending the LSTM-based ingredient encoder with TF-IDF semantics indeed leads to improved performance on retrieval quality. And by adding the TF-IDF-based feature engineering to 2 or 3 components of recipes will yield better improvements than only adding to the ingredient. Therefore, we use JE plus TF-IDF in the rest of the experiments to refer to the TF-IDF semantics enhanced recipe embedding approach. This figure provides the visualization for comparing JE baseline with JE plus TF-IDF. For the recipe to image query, the first row shows the top 5 images retrieved by JE, and neither noodle nor tofu can be found in these 5 images. The second row shows the top 5 images returned by JE plus TF-IDF with the matched image as the top 1 result, showing that JE plus TF-IDF is effective and can yield the key ingredient extracted from the recipe. For the image to recipe retrieval example, JE plus TF-IDF found the matched recipe in the top 3 result. And the JE returns the matched recipe as the top 41 result. Note that no image category semantics is used in both JE and JE plus TF-IDF. After getting the semantics enhanced recipe and image embeddings, we can start the joint embedding learning to reduce the distance between the matched recipe image pairs iteratively. Most existing works tend to use two types of loss functions to perform the global joint training, which are primary loss and auxiliary loss. A primary loss function is typically defined by a distance function to measure the similarity between the textual embedding and the visual embedding in the joint latent space. Euclidean distance and the cosine distance are the most popular ones. As for the auxiliary loss functions, they are mostly used to add cross-modal semantics to enhance the joint embedding optimization. Some of them need to utilize the categories labels for recipe image pairs in the dataset. However, the food category labels used in JESR approach are not so good, which are obtained from the category labels in food 101 dataset, and the background analysis results on recipe titles over the recipe 1 million dataset. Only about half of the recipe image pairs can get valid category labels due to the lack of title matching to a real category label, while the rest will be given a background category. NSJ improves the category assignment algorithm by additionally considering the recipe ingredients, instruction, and food image feature to do the category assignment. Every recipe image pair can get a reasonable category label in NSJ's category assignment algorithm. The table below shows the results of comparing these two different category assignment algorithms on the 1,000 test set based on the JE baseline. The results show the performance improvement can be yielded by using the category assignment algorithm in NSJE. This figure shows the visualization of using the two different category assignment algorithms. For the recipe to image query on the top, JESR assigns the background label to the query recipe and returns the matched image in the top 41 result. In comparison, NSJ assigns a category label, pineapple salsa, to this recipe, which is reasonable for the querying recipe, showing a reason that the NSJ returns the real matched image as the top one result. A similar observation can also be found in the image-to-recipe retrieval results, showing that joint embedding with high-quality category semantics can yield better cross-modal retrieval performance. Next, we will introduce the combo of 4 primary and 3 auxiliary loss functions. Now we start with the primary loss functions. The pairwise cosine similarity loss is used to minimize the cosine distance between the matched image recipe pairs and maximize the distance between unrelated pairs. In some recent works found, the triplet loss is much more effective to optimize the joint embeddings, since it can bring the positive instance closer and push the negative instance away at the same time, while pairwise loss can only consider pairwise instance at a time. And the triplet loss with soft margin is a variant of triplet loss, which adopts the soft plus function to replace the hinge function in the original triplet formula. Circle loss reweights the distance between anchor instance and the positive instance, dp, and the distance between anchor point and the negative instance, dn, instead of treating them equally in the standard triplet loss. Here are some representative auxiliary loss functions. Semantic regularization loss imposes a regularization term such that the learned recipe and the image embeddings will be penalized if they fail in performing the food classification. Category-based triplet loss is used to reduce the distance between the pairs sharing the same category and separate the recipe and image embeddings that belongs to different categories. Modality alignment loss is used to optimize the alignment between the embedding from the two modalities. When given an embedding from one modality, We hope the chained discriminator cannot distinguish whether the feature embedding is generated from food image or recipe text. Here are some examples of combination of primary loss and auxiliary loss. In the following experiments, we use the semantics-enhanced recipe and image embedding in NSJ approach by default, and only switch the loss functions. This table shows the results of using different combinations of primary loss and auxiliary loss. We observe that the combination of using triplet loss with soft margin as the primary loss and the semantic regularization loss, modality alignment loss, and the category-based triplet loss as the auxiliary loss outperforms the rest of the combinations. Another interesting observation is that ANSR and NSJ both leverage the discriminative words during the recipe embedding process, with ANSR adding attention mechanisms and NSJ adding TF-IDF semantics. And the results show that TF-IDF approach outperforms the attention mechanism. This figure provides visualization results of the recipe to image query, showing that a careful combination of a primary loss function with the auxiliary loss function can further boost the overall performance, in addition to incorporating semantics-enhanced modality-specific embeddings. To conclude, three different semantics are incorporated into the recipe embedding, image embedding, and the joint embedding learning process. The recipe TF-IDF semantics are utilized to capture the discrimination significance of each ingredient in its recipe. The image category semantics are leveraged to align the image embedding closer to the matched recipe embedding in the common latent space. And the category assignment algorithm is improved in NSJ to generate category semantics with higher quality, which is incorporated in the joint embedding optimization. Besides, we evaluate different combinations of primary loss and auxiliary loss and analyze the interaction between the different kinds of modality-specific semantics and the different loss functions. For future work, we are trying to find other text and image datasets to see if this type of semantic tuning can still be applied and boost cross-modal retrieval performance. That's all for today's presentation. Thanks for listening.